Hey everyone, in this video we're going to start our discussion of the precise definition of the limit. So this is part one of the series of videos for the precise definition of the limit. We'll start with this example. The figure shows the graph of a linear function with f and the limit as x goes to 2 of x is equal to 3. So then this is our function f of x, and we have that the limit as x goes to 2, a two-sided limit, is equal to 3. So let me highlight that part. Now notice here that f of 2 does not exist, right? F of 2 is not defined because we see that there's an open circle there, so that means 2 is not in the domain, but everything around it is defined. So the only thing is that when x equals 2, there's no y value. It should be 3, but it's an open circle there, so it's not defined. So we can say 2 is not in the domain of f of x. So, but the limit as x goes to 2 of f of x, we know it exists, is equal to 3. We're given that. So that's, again, just to review limits, right? The limit can exist even if the function value does not. So let's look at what we're tasked to do. So it says for each value of d greater than 0, determine a value of c greater than 0. So both positive values satisfying the statement the absolute value of f of x minus 3 less than d whenever the absolute value of x minus 2 is between 0 and c. And then given these values of d. So what does that mean? What are we supposed to be doing? For each value of d, so we're given the value of d. So d equals 1 for part A. So when d is 1, determine a value of c such that when the absolute value of f of x minus 3 is less than 1 for part A, the absolute value of x minus 2 is going to be between 0 and the c that we find. So let's see what that is. And let me copy this graph and put it down below. Maybe we should also review what absolute value means. So when I have the absolute value of f of x minus 3 less than d, what is that really saying? Now remember, f of x these are y values. So what this is really saying is that the distance between, remember, absolute value means a distance. So the distance between x and 3 is, in this case, less than d. So that's why an absolute value. An absolute value is always giving you a distance. And so this one, what does the one for the x say? So when I have 0 is less than absolute value of x minus 2 less than c, in terms of distance, this says the distance between x and 2, right? X and 2 is more than 0 but less than c. So I'm going to say less than c and more than 0. Which is kind of understood with distance. Distance can't be negative, but for the precise definition, as we get into the algebra of this, we want to make sure that we have the 0 there to indicate that we want the distance that is the positive. So that's what this really means. So let's go back to this. So when d is equal to 1, so the distance between f of x, I put x in here, f of x and 3 is less than d, and we said the f of x are y values. So for d equal to 1, let's see what that means. So when d is 1, I'm going to go the distance between the y values, f of x and 3, is less than 1. So that means that I'm going to go, there's 3. So if my d is 1, I can go as high as 4 and as low as what? As low as 2. Right, my distance, it says the distance between f of x and 3 is less than 1, less than d. So that means that D is somewhere in here. So all these Y values, so let's see where they put us for the X values. So if you follow this to the function, where do they land? So follow that all the way down. This gives me X equals 4. So what this is saying is that whenever I want to satisfy the statement when the Y values in 3 are a distance less than 1, then my X values are a distance of C away from 2. So I'm looking at 2 here, right, when X is 2. And then what's the distance between 2 and this value that I just found? So my distance here is 2. So it looks like C might be 2, but let's see what happens on the other side. So when I am between the Y values between 3 and the Y value is less than 1, then we land over here, which is 0. And so what is this distance? So that is also 2. So that means that when for D equal to 1, our C value is C equal to 2. So that's why it's important to understand that the absolute value is talking about the distance. So the distance between the Y values and 3 is less than D. We should have then the distance between the X values and 2 are less than C. So when D is equal to 1, when the distance between the Y values and the Y equals 3 are less than 1, so between 2 and 4, our X values are between a distance of 2 away from the X value of 2. So let's try the same thing for, what about for D equal to 1/2? All right, so for D equals to 1/2, we want to make sure that we satisfy this statement. The distance between the Y values in 3 is less than 1/2 now. So let me write that down. So we want the distance between the Y values in 3 to be less than 1/2 whenever the distance between X and 2 is less than C. So we're looking for that value of C. So let's see. So let's go to the Y values, right? F of X is just a fancy name for Y. The Y values in 3. So when I'm over here, here's Y equals 3. So when we're 1/2 from it, so we don't go all the way to 4, now we just go to there, to 4.5, not 4.5, 3.5. And so that will be a distance of 1/2 away from 3. So there's 3, and then 1/2 the other way. So that will put me at 2.5. So that is also a distance of 1/2 away. So where does that put us? So I'm gonna highlight where it takes us. So when I'm 1/2 away from 3 along the Y's, where does that put us for the X? How far away from 2? So it looks like 1 away, and then on the right, then when I'm at 2.5, looks like we hit the graph there, so we go to 1. So the question is, what is the distance from 2? My distance now is 1. So I'm a distance of 1 away, so that must be the C that I'm looking for. So therefore, C is equal to 1. And so I can say this statement is satisfied. So when D equals 1/2, C equals 1, and then we have this statement is satisfied. And so that's kind of the idea of the precise definition of the limit, is as we get close to the Y values, there are specific, we have to be within a specific, we call it a neighborhood of X. So when X is, we have to be within 1 of 2 in order for us to be within 1/2 of 3. And so obviously you can see that the closer we get to 2, the smaller this distance get, then the closer those Y values are going to get. So the smaller the c gets, the smaller the d is going to get. So let's look at the precise definition of the limit. So our precise definition of a limit is that when we have a function defined in some open interval that contains the number a, except possibly a itself, then we say that the limit of f of x as x approaches a is L, and we write what we're used to seeing, right? The limit as x goes to a of f of x equals L if for every number epsilon greater than 0, there is a number delta greater than 0 such that this inequality happens, right? The distance between x and a is between 0 and delta. If that happens, then the distance between the y values and the limit is less than epsilon. So this is the idea that we were going over in here. So the smaller our distance from the a or x value, as the limit gets close to a, we want the y values to be really close to the L, the limit value. How close? Very, very tiny distances. So this epsilon and this delta are very, very, very small numbers. So here I use kind of large numbers. We use epsilon, called a d here, is 1, and we were trying to find the appropriate delta or c to go with it. But ideally, and then here I use d equals 1/2, which is the equivalent of epsilon in our definition. But we want these distances to be really, really small, really, really close to 0. We want those to be close to the value of the limit that we're going for, right? As x goes to a, so I want to be really close to a, so I want that delta to be small, and then this epsilon should be small as well. So let's try an example. So here's our example. So use the precise definition of a limit to prove that the limit as x goes to 3 of 2x plus 1 is equal to 7. And so we're going to use our precise definition here. I really, really encourage you to, if you use flashcards, 3x5 note cards, write this in your note card. We want to memorize it. We want to be able to understand what this means. So the main thing that we're going to use from this definition is this part. For every number epsilon greater than 0, there's a number delta such that this inequality happens. So let's dissect that for our example. So limit as x goes to a of f of x equals L means, and this is when anytime you see one of these problems, you should be rewriting the definition. I find it really helpful to write the definition of what it means for this limit as x goes to a of f of x to equal L, what it means in order to go through the proof. So what this means that for any, so given any epsilon greater than 0, we can find, so there exists a delta greater than 0 such that, and this is our if statement, so if the distance between x and a is less than delta, then the distance between the y values and our limit is less than epsilon. And so what do we need to find? So this is what our definition says. Some of the things that we need then are, we need a, what else do we need? We need f of x. I don't know why I'm putting them in quotations, but now I gotta be consistent. And we need L in order to use this definition, right? So let's look at this. Limit as x goes to a, so a must be 3 of f of x. So f of x must be 2x plus 1 and equals L. So L must be 7. And so now we can start to put it all together. So I'm going to write my proof here. And usually I do a little bit of scratch work in order to find our delta that corresponds to the epsilon, because this is for any epsilon, we should be able to find a corresponding delta. So going back to that example, right, for any epsilon, here I called it d. So when d equals 1, we found the delta, right? So here, this is my epsilon equals 1. We found the delta value, the corresponding delta is 2. And then when epsilon is 1/2, so that's why the definition says, given any epsilon, so for any epsilon, so when epsilon was 1/2, what did we find? We found, so here, when epsilon was 1/2, we found our delta to be 1. So given any epsilon, you can find the delta for it. So if I say, for this example, if epsilon is 1/8, could you find the corresponding delta? Yes, looks like it's double the epsilon, right? So it would be 1/4 likely without doing the work. So here, for any epsilon, given any epsilon greater than 0, we should be able to find the corresponding delta such that this happens. So the way we're going to start the proof is we're going to say, let epsilon greater than 0 be given. Right? So that, think back to that first example. So epsilon's 1, epsilon's 1/2, and I just gave you 1/8. So given for any epsilon, so let epsilon greater than 0 be given, we're going to choose a delta to be something. In this something, we have to find it. So we're going to do a little bit of scratch work in order to do that. And then our if then statement comes in, right? So if we can find that delta, then this is going to happen. If x minus a is less than delta, then f of x minus l is less than epsilon. So we're going to assume that 0 is less than x minus a. What's a in our case? 3. So the distance between x and 3 is less than our chosen delta. So we're going to come back, fill that in. Then our f of x minus l is going to be equal to something, and we're going to do some math here. All right, so this is the setup for our proof, but we need to find that delta, right? What is this guy? What is that delta? So in order to find that delta, we're going to do some scratch work. This is really, really important. So we're kind of going to work backwards. So we're going to create some scratch work. And so what we want, what is it that we want? The then statement. We want the absolute value of f of x minus l from our definition to be less than epsilon. So that's what I want. So I want f of x minus l to be less than epsilon. So I'm going to start with that to try to find the delta. That's essentially what we did here. Epsilon was given. Epsilon was 1/2, and I went and found the delta. Delta was 1. That's what we did up here too. Epsilon was given. Epsilon was 1. We went and found the delta to be 2. So that's our scratch work. What we're going to do, we're going to put the epsilon, and we're going to go find the delta. So this is what I want. So that means in our function terms, I want, what was our function? 2x plus 1. So I want the absolute value of 2x plus 1, and then minus l. So minus l is 7 to be less than epsilon. And so this is 2x minus 6 less than epsilon. And then notice that here I can take out a 2. So everything's positive. Well, the 2 is positive if I take it out. So I'm left with x minus 3 less than epsilon. And hopefully by now you see, like, wait a minute, there's that absolute value, x minus 3. That's the absolute value of x minus 3, the distance between x and a. And so I can say, oh, then the absolute value of x minus 3 is less than epsilon over 2. So guess what? We're going to choose delta to be epsilon over 2. Based on this, given any epsilon, I can backtrack my steps to find the delta that goes with that epsilon. That's what we did here. Epsilon is 1/2. Find the delta that goes with that. So now, right, this is just that we're saying any epsilon. So I'm not giving you specific numbers, I'm giving you a variable for epsilon. But given epsilon, I can find delta. So if epsilon is 4, delta is going to be 4 over 2. If epsilon is 1/2, delta is going to be 1/2 over 2, and so on and so forth. And so now we go back to our proof. And so we're going to say choose delta equal to epsilon over 2. Assume 0 is less than x minus 3 less than delta, epsilon over 2. Then, and now we kind of redo our scratch work here. F of x minus L, our goal is to show that f of x minus L is less than epsilon. So then I'm going to say the absolute value of f of x minus L is equal to the absolute value of 2x plus 1, that's my f of x minus 7, which is equal to the absolute value of 2x minus 6. So notice that I'm kind of redoing my own scratch work. Factor out the 2, and I'm left with this. But now our assumption comes in. I know that the absolute value of x minus 3 is less than epsilon over 2. So I can use that in here, right? Since the absolute value of x minus 3 is less than epsilon over 2, that means that 2 times absolute value of x minus 3 is going to be, notice that here I have equals. Now we're going to say this is going to be less than 2 times epsilon over 2. And so these 2's cancel, and I'm left with epsilon. So therefore, I was able to prove that the absolute value of f of x minus L is less than epsilon. And that finishes our proof. I know, it's a lot to take in. So I do have one that I want you to try on your own and see how you do. And I will help you set it up. All right, so we have this example. So on your own, try, prove that the limit as x goes to -2 of 3x plus 7 is equal to 1. So in order to use our definition, right, write yourself, what does it mean to say the limit as x goes to a of f of x equals L? So this means, and then write out the definition, and then find out what is a. So a in this case is limit as x goes to a, is what our limit is going to. So a is -2. What's f of x? F of x is what am I taking the limit of? So that will be 3x plus 7. And lastly, what is L? L is what is equal to, so L is 1. And so this is where I wish there was a stamp that you could buy at the bookstore and just say, oh, okay, so my proof is I'm going to let epsilon greater than 0 be given, right? Someone gives you an epsilon, you are tasked to find the corresponding delta. So let epsilon greater than 0 be given, we're going to find the delta, and that's going to come from our scratch work. So choose delta equal to something from our scratch work, and then we're going to make the if assumption. So assume that the absolute value of x minus a, well, a is -2, so this is going to be minus a minus 2, is less than delta, whatever delta is. So it's going to be 0 is less than x plus 2 in this case, because minus a minus becomes plus, less than whatever you chose your delta to be based on your scratch work. Then the absolute value of f of x minus L is equal to what? And so how are you going to set up your scratch work? We want, what is it that we want? We want f of x minus L to be less than epsilon. So you're going to start with your f of x, 3x plus 7, and then minus L, so minus 1 less than epsilon, and go from there. So what I'm going to suggest is that as you get to the bottom of this, you should have your delta equals to something. go back, put it in here, and work out the proof just like I did in this example. All right, so I'll end this video there. Part 2 of this video will get into a little more complicated limit proofs.